some lengths. Here, 2 and 2, so 4 meters total. 2, and this is 1.5, so I have a 3, 4, 5 triangle. That's going to be 1.5 meters. Okay, and a loading, like a distributed loading, that goes all the way across here, like this, and that has an intensity of 300 newtons per meter. And what I'd like to do is determine the deformation of point D. All right, so there are a couple ways to do this, but what we want to do really, if you didn't know the axial deformation equation, so this axial deformation equation is this, you might remember the sum of NL over EA, and delta is equal to 0 to L n of x dx over E ax. So these are our axial deformation equations. So we need to find essentially the deformation of this rod BC, and then see how far down point B goes, and then use similar triangles to find how far point D goes. Yeah? Yeah. All right. And so that's going to start, if we didn't know this, we calculate the stress, the strain, the deformation, and then use geometry for D. Here, ABD is rigid, so ABD is a rigid beam, so at least we know that it doesn't have some sort of curvature to it, so we're neglecting the curvature in this case. And so the first thing I want to do is cut and draw a free body diagram, and so we'll just cut it here. We'll cut it here. Let's see, I have a pin. Let's see, I'll just draw a pin AY, AX, and then if I cut through the rod, right here, like this would be NBC, I believe, NBC, and really all the attention is in the rod. I can calculate AX and AY, but I actually don't need it in this problem. And so here too, I'm going to use equilibrium equations for NBC, and really I just need one, and that would be some of the moments about A. So for some moments about A equal to 0, boom, like this, I would get, here just a quick reminder, this was a 3, 4, 5 triangle, so I would have, let's see, NBC, the vertical component would be 4 foot, and the arm is times 2 meters, minus the force resultant of the distributed load, which is 300 newtons per meter, times 4 meters, which will give me the force resultant, and the arm, the resultant is right here. The 1200 newtons is right here, so the arm is 2 meters, and all this equals 0. And let's see, I can do some math very quickly, and the 2 meters cancel out. Dude, I can print this and give it to you too. Anyway, so it's all good. It's in color. I'll print it in color. Like 12 cents a copy. No! And then the 4s either cancel out. Wow. And let's see, the meters here cancel out. Yay. So, shoot, NBC looks like it's going to be 1500 newtons. No, oh snap. Is that right? Yeah, I did right. Yeah, who knows? We'll see. If I make calculation errors. Is it 3 over 5 or 4 over 5? Oh snap. I messed up. It's 3 over 5. Thank you. This is why. No one is perfect. And in the words, don't judge me, judge yourself. 300 times 4 meters. Alright. So that 4 doesn't cancel out. So then NBC in this case would be, let's see, 5 4 is 100. Was it 2,000? 2,000? Yeah, 2,000. I think 2,000. Dude, you can come in if you want. Sorry. No, I'm recording, so don't see. It's office hours. It's confirmed. We should do homework. Yeah, sorry. Oh, alright. Sorry about that. Oh, no. Let me pause. Okay, we're back. It's almost 12. Oh, snap, I got a meeting. Okay, so NBC at 2,000 newtons, we're going to go faster right here. And then you know what I could do to get the deformation of the rod BC? If I have learned the axial deformation equation, this is NL over EA right here. And so the deformation of B with respect to C, I could go straight away. Deformation of B with respect to C is 2,000 newtons times the length, which was, let's see, 1.525, 2.5 meters. The initial length was 2.5 meters. And then I have the modulus of elasticity of aluminum, which we're saying is 69 gigapascals, which is 69 kilonewtons per millimeter squared. And then the area is 14 millimeters squared. Yes. And then so I think, in terms of units, so I don't make any units mistakes, I'll rewrite that 2,000 newtons as 2 kilonewtons. And this should give me an answer in meters if I plug and chug. So 2.5 divided by 69 divided by 14 is 5.17 or 18 times 10 to the minus 3 millimeters, which would be 5.18 millimeters. Yes, that would be delta. If we didn't know this, and then I would apply it, I would calculate the stress, and that would be in BC. I would calculate the normal stress, and so that would be sigma BC is equal to NBC over the area of BC, which would be 2 kilonewtons divided by 14 millimeters squared, which would be 2 divided by 14, and that would give me 0.143 gigapascals or kilonewtons per millimeter squared. Yeah? Okay. And then I would apply Hooke's law. Hooke's law. Another way would be Hooke's law. And you know, the reason this is working is because the way we derived this relationship right here was with normal stress and Hooke's law, right? And the definition of strain, but it's all good. And so here, by Hooke's law, which is sigma is equal to E times epsilon, I can get the strain in, is it BC or BD? It's BC, right? Yeah. BC is sigma BC over E, the modulus of elasticity of alumina, which would be 0.143 gigapascals over 69 gigapascals, and that is divided by 69, 2.07 times 10 to the minus 3 strain, which is millimeter. We'll just call it millimeter per millimeter. Yeah, that was good. Your business. That's good. That's excellent. Okay, and then by the definition of strain, for strain definition. Look at anyway, strain definition. By the definition of strain here, I would have let's see, epsilon BC is delta BC over the original length of BC, and so delta BC, the change in length of BC, is 2.07 times 10 to the minus 3 times the original length, which was 2.5 meters or 2,500 millimeters, and that would tell me times 2,500 is 5.18 millimeters, just like before, the other way. Yeah? Okay? So it matches, life is good. Okay, so I have the deformation of BC. Okay. Now I have, if you need to go, you go. But it's all good. I know, because I explained that, right? Yeah, I did, right? It's all good. And so now I look at the geometry of deformation to answer the question, the geometry of my structure. I should do that. Every time I say the word structure, I go like structure. So here, it should be like, boom. Here's the initial geometry. Yes, here's the initial geometry. Oh, yes. So it was here, and here. And then the thing deformed. So I'll use a different color for that. How about I use green? There's the beam, rotates down after I load it. So it goes here, like this. And let's see, I would put in orange. The cable or the rod also goes straight down because my deformations are small. And this, a little bit off, that's all good. This is this right here. And the orange line is the final length of the rod BC. So LFBC is the initial length plus delta BC, which would be 2,500 plus 5.18, so it's 2,505.18 millimeters. That's the final length. The initial length was 2,500 millimeters. And then here, this length was 1,500 millimeters, and this deformation right here is really, we meet this one. We want to know how far down did it go, like this. We want this distance right there. And that is delta of point B right here. And we would use similar triangles to find delta B, the displacement of D. So we have a couple choices. We could use the law of cosines for this black, blue, orange triangle, right? That's one way. Another way might be, like if I look at this green, blue, orange, that's a right triangle, right? And so this distance here, and this distance right here, I'll call if I call this like capital Y, right there, you know, I could say that, oh, and this distance we know is, what is that distance? 2 meters, or 2,000 millimeters. 2,000. I wonder if this might be not as accurate, because it's all good. It's all good. And by that, small deformation, and so y squared plus 2,000 millimeters squared equals this final length, which is 2,505.18 millimeters, quantity squared, and then I can solve for y, whatever that is. All right, that is minus 2,000, and it's for root. Okay, I think I got y is 1,508.62 millimeters right here, so that means delta B is y minus 1,500, which would be 8.62 millimeters. Yeah? Yeah, okay. And then by similar triangles, from this black, blue, blue, by similar triangles, and triangles, I would get that delta B over 2 meters is equal to delta B over 4 meters, and delta D would be 2 times delta B, which would be 17.24 millimeters, and that downwards. And that is it. Yeah? All right. Alright, what's up everyone, welcome back. District 3, office hours. And in this problem, we're going to do a problem with, let's see, the system here being supported by this wire here and this distributed load. And the diameter of the wire before loading is 0.2 inches. After we apply this distributed load W, the diameter of that wire is 0.1999 inches. And we would like to find out what this load W, this distributed load W is that we applied on the beam at BC. So I have the properties of steel here, 29,000 KSI for the modulus, 50 KSI for the yield strength, and then 0.3 for the Poisson's ratio. And I'm going to use, I'm going to work backwards essentially. I'm going to go here, I have the change in diameter of the wire. I'm going to use that to calculate the lateral strain, and then I'm going to use the lateral strain and Poisson's ratio to calculate the longitudinal strain. And then from there, I should be able to use the Hooke's law to get stress. And then from Hooke's law, I should be able to get the normal force in AB. And then with that normal force in AB, I should be able to apply equilibrium equations and get W. And then there you go. I'm done. All right. And in fact, I don't need to do this video. You're good. Right. things here. So here too is the, let's do a strain analysis. Strain analysis, we'll call that. All right, the value of the strain. And what I have here is that this wire has an initial diameter of 0.2 inches. And then I the load is applied and the diameter shrinks right here to 0.199 inches. 9 inches right here. And I can calculate the lateral strain here. Epsilon lateral would be the change in length over the original length, change in diameter over the original diameter, and this would just be 0.1999 inches minus 0.2 inches divided by 0.2 inches, which is negative 0.0005. Negative 0.0005 inch per inch if you want units to it. Okay, and that is my strain there. And now to get the longitudinal strain, so that I can relate it to the normal stress, would be this by the definition of Poisson's ratio. And so Poisson's ratio is the negative of the lateral strain over the longitudinal strain. So in this case, this is equal to 0.3. And so now if I substitute to find the longitudinal strain, I would have negative times negative 0.235 divided by 0.3 is equal to the longitudinal strain. And I would get for the longitudinal strain negative 0.00167 inch per inch. Yes. Okay. And now I have the longitudinal strain, which means I can go ahead and calculate probably the stress in the wire right there. So 1, 2, 3. I can use Hooke's law for normal stress in AB, in that wire AB. And there I would have, let's see, that Hooke's law is sigma is equal to E times epsilon. And again, the normal stress and then that longitudinal direction, so we're using longitudinal strain. And this, we're just going to take 29,000 KSI times 0.00167 inch per inch, which is, let's see, calculate 48.43. And we're good here because KSI, and this is less than the yield strength of steel, therefore we're still in the linear elastic region. We're not experiencing permanent deformation in the wire, so we have to yield it. Otherwise, if we yield it, we have to do maybe a different type of analysis. Okay, and here, so we have that stress, and then we can look at the definition of normal stress with due to normal force, which is that here, sigma is equal to N over A, and that normal force in AB is equal, divided by the area of the wire, the cross-section wire AB, is equal to 48.43 KSI. And now I can just go ahead and by def here, NAB, that normal force in AB is 48.43 KSI times the area of the wire, which is, we'll go with engineering stress, so we're going to use the initial area. Okay, so here we're going to use that initial area of the wire, which will be pi over 4 times the diameter, the original diameter of the wire squared. So here, pi over 4 times 0.2 inches squared. And this is like, I got 1.52 kips. Alright, we got a verification. Hey. Alright, 1.52 kips. Alright, and for those of you that are not in the USA, using kips, that's 1,520 pounds. Alright, so now we have the force of the rod or the wire here that's caused by this distributed load. And then now we just go back to basic statics here. And if I, 5, I'm going to use a free body diagram and equilibrium equations to determine loading, to determine W right here. And so, you're used to using equilibrium equations and free body diagrams to relate the external load to the internal load, but now we're using it to relate the internal load to the external load, which I guess does the same thing. Alright, so here is my structure again. Yes. Like this, and I have that cable here for the wire, and that wire would cut through the wire. It reveals a normal force in tension right here, this NAB, which we know is equal to 1.52 kips in tension. And we have a distributed load, W, right there, a distributed load W right here. And in the previous drawing, right here, this was 60, this is 90, so this angle right here is 30 degrees. Okay, so I can go back here, and this angle right here is 30 degrees, and I know this length is 9 feet. To get the distributed load directly, I can do that with one equation, or one equilibrium equation. If I think wisely, I can just use one equilibrium equation to get the distributed load directly. And what equilibrium equation do you think that is?